Let's see what we covered in the class. We go into the second most important engineering property. We call it as compressibility of the soil. And when you apply loading, what happens to the grains? Can you see here? The grains are all packed with larger voids here. The void spaces are high. So when you apply the load, the particles will try to readjust. And you can see the different mechanisms. The particles can slide, they can rotate. In case of clays, of course, they do bend. But what you find here is you have large void spaces. Please imagine this is highly magnified. And what is happening to the void spaces? They are becoming much smaller. So because of that, when the original height of the sample is here, after compression or after loading, the sample decreases in volume. And this is how you get the settlement or compression in the soil. Please note that the particle sizes don't change. The order of stresses we put in are very small compared to the elasticity or strength of particles. Unless you have a 300-400 meter dam, the particles are not going to get damaged. So the size of the particle is the same, only the void spaces reduce, and that is why we get compression in case of soils. So just look at a very wide embankment, and I have a compressible layer here. Soil layer 1 is not that compressible, but 2 is highly compressible. What is the thickness of the layer compared to the width of the embankment? Very, very small. So can I say that all the deformations in the center except the near the edges will be all one-dimensional? A particle cannot move laterally because there is another element which is also trying to move laterally. So because of this requirement, you will have predominantly or only one-dimensional compression. So if I want to simulate this embankment loading on this clay layer, the embankment may be 30-40 meters wide, clay layer may be 2-3 meters thick. That I can do by means of provide a ring. I put the sample here, and you can see that the diameter of the sample is much higher than the thickness, plus I am putting a rigid ring here. So if I put the rigid ring, there can be no lateral deformations. And if you want to saturate the sample, you put the whole thing inside a cell, fill it with water. You have a porous stone here, another porous stone here, and we apply the load. We put the dial gauge to measure the displacements. So this is how a one-dimensional compression is simulated in the laboratory. So this is the detail of the same, and you can see here the load is applied, and I have a dial gauge here, and here is the soil sample, a porous stone, and this is the loading cap, and here is a beam through which I apply the load. So this beam will actually transfer heavy load, and this is a dial gauge. Usually we have only about 0.1 millimeter as the accuracy. And here is the reading. When I put the dial gauge here, this reading keeps rotating or moving, and we take the readings at different times. Same thing, porous stone, and you can see here now the filter paper also, so that the soil from here cannot go into the porous stone. And the load is applied. The mechanism here is, in the lab you will find a series of these odometers or consolidometers on one rigid platform, and the load is applied by means of these levers. You can put a smaller load, and you know the physics of it. A lever can multiply the load very large. So if I put a certain 10 kg, the lever ratio is 11, so it becomes 110 kilograms. So the stress on the ring or the sample is very high, and here is the fulcrum here, and so you can simply use the principle of levers to transfer heavy loads by this lever mechanism. This is the odometer test, a very simple illustration. I have two pans. Initially I put smaller weights here, and I start putting heavy weights, and they get multiplied and apply the load onto the sample here. Why do we do that? To determine the stress strain time properties, particularly of saturated soils under sustained load. when you build a structure, it's going to be there for hundreds of years. So it's a long-term monotonic loading. We can study the phenomenon, and we also study with respect to time. Unlike steel and concrete or other engineering materials whose properties are not time dependent, once water deformation is final and you don't have to worry about what is the deformation after 1 year, 2 years, 10 years. In case of soils, the deformations are time dependent, so we measure that. We take a small diameter sample, and if you want a real good sample, we take undisturbed one from the side, put it inside the loading device, and apply the load in increments, which I told you in small increments. And what happens? There will be no horizontal displacement because this is a rigid ring. In the field also there is no horizontal displacement. So what you will have is only a vertical compression. Whether it is volumetric or axial, it's exactly the same because the area is constant. And if you look at the stress path for this test, it goes along the K0 line because there are no horizontal deformations. And if you look at the data, what we plot is void ratio against vertical effective stress. You can see that initially the deformations are very high, and as you increase the load, the deformation becomes smaller. So the curve is concave to the right, and this is how it looks like. If you unload, you can see only very small recovery takes place. Suppose I started unloading from 10 kg per centimeter square, it's coming back. When you reload, it is trying to come back close to that. There is a slight hysteretic effect, but that's generally not very significant, and then it goes back. So this is how the loading looks like, and this is how unloading looks like. And if you take the slope of this line, is defined as coefficient of compressibility defined by the symbol A sub V. It's equal to change in void ratio by increase in the effective stress, vertical stress. And this is how we define the parameter.